In this video, we describe the BigDAWG Polystore system version 0.1. This work was sponsored by the Intel Science and Technology Center for Big Data. Before I begin, I'd like to acknowledge our numerous collaborators from a number of institutions. I'd like to include researchers from Intel, Brown University, Carnegie Mellon, MIT CSAIL, Northwestern University, Portland State, the University of Chicago, University of Tennessee, as well as the University of Washington. So let's get started. What is the challenge that we're trying to solve? We know that data comes in all shapes and sizes. I've worked with a number of data corpuses, and they often contain, within the same data corpus, unstructured data, relational data, imagery, time series, could be video, etc. The traditional technique of forcing all data to fit into a single data store is inefficient and in many organizations infeasible. We believe the idea that you should leave data in the storage engine that matches the data, and this is a concept that we call a Polystore system. Now, Polystore systems build upon a lot of great work that's been developed by the federated and parallel database community. Federated databases were all about mapping disparate database management systems via a single query interface. These systems often were characterized by a single query language or a single data model, such as SQL and a relational data model. There are numerous examples, some of which are Garlic, R, IBM DB2. Parallel databases, on the other hand, were all about having a single logical database or tables that were divided over multiple computing elements. These databases have been quite popular, and we've seen a number of examples coming up in the past few years. Some examples are SciDB, which is an array parallel database, and Teradata, which is a relational parallel databases. Polystore databases, on the other hand, are designed to simultaneously work with disparate database engines and programming and data models while still supporting the complete functionality of the underlying database management systems. And today I'm going to be discussing the BigDAWG Polystore system. BigDAWG is all about bringing together advances in data management. So we've worked with a number of people in data analytics and processing platforms, people who have been developing scalable math and algorithms, folks who are developing new visualization techniques for big data, as well as those who are developing new hardware architectures that can be exploited for fast and efficient data management. The BigDAWG system, and BigDAWG here stands for the Big Data Working Group, is all about integrating these advances in big data across multiple data processing systems, and we've validated the BigDAWG Polystore system by developing benchmarks and testbeds and working with researchers in the medical and oceanographic community. So BigDAWG is a large-scale project meant to change the way we interact with very large data sets. The BigDAWG system is our reference implementation of a Polystore database. We've designed it to support high-performance ingest and analytics and many of the relative advantages of different database systems that are out there. In our design, we've ensured that we support the often competing notions of location transparency and semantic completeness. And this allows us to really develop a scalable and flexible architecture. In doing so, we've developed a number of foundational operators. We've developed a common interface, a number of common analytic translators via shims, common data translators via cast operations, and been able to support multiple databases in native languages via the concept of islands. I'll talk about a couple of these pieces. In the middle of the BigDAWG architecture is the BigDAWG middleware. And the BigDAWG middleware consists of four pieces. There's an optimizer, a monitor, an executor, and the migrator. A user, which is developing a visualization, client, or application, issues a query to the BigDAWG common interface. This goes to the optimizer, which works with the monitor to determine the optimal query plan for a particular query. This complete plan is determined and sent to the executor, which is responsible for physically executing this query on the different database engines that are present. The executor, in a query plan that's sent to the executor, may rely on disparate data sources and may need to talk to the migrator, which is responsible for transferring data across different systems as needed. The executor, once it completes the query, returns an output back to the visualization, client, or application. Another important component of the Polystore system is the concept of islands. And in our world, islands are the trade-off between functionality or semantic completeness and location transparency. Islands have their own data model, a language or set of operators, and a set of candidate engines. And in the current version of BigDAWG, the user specifies the island. Islands do essentially an intersection of what separate engines provide, and BigDAWG does a union of what these islands can provide. And in most cases, these islands may be logical. The 0.1 version release of BigDAWG consists of support for a number of islands and database engines. Specifically, we support a relational island, an array island, and text island, and we include support for database engines such as Postgres, Accumulo, and SciDB. We hope you will take these islands and database engines to develop new applications such as data explorers, visualizers, or deep analytics. Finally, I'd like to acknowledge again the Intel Science and Technology Center for Big Data, and a big thanks to our collaborators and numerous members of the ISTC Big Data team.